In problem 10.45, we have a small 10-gram bug. See it listed right there. It's at one end of a thin uniform bar. It's at the end of a table. So let's draw that up here. Here's our big table. Okay. There's a bar here. That might be able to draw. There we go. Supposedly that's thin and uniform. And there's going to be a little bug at the end of it. We'll draw our bug. Okay, there's our bug. Give him some little arms and legs, so it's a little scary. Looks kind of like the sun there, so it's not great. Okay, and it's pivoted. There's going to be a pivot at the end of the table. So this end is actually fixed. It can't move there. Okay. So let's pivot. Okay, I put the X there only to remind us that it's not going to move. Okay. And what's going to happen is our bug is going to jump off the end of the table. It's going to go this way at 20 centimeters per second. Okay, and normally, if the end wasn't fixed on the right, the whole bar would just kind of slide the other way and rotate. But it is fixed at the end, so we're not going to be able to just slide. The only choice that the bar is going to have is to rotate, and it's going to rotate like that sort of way. Okay, and so it's going to have an angular speed as it rotates, and we're going to figure out what that is. That's what our goal is. We're going to find out what the angular speed is. Okay, so we have no idea. So we're going to find that out. Again, our linear momentum, not conserved. Our angular momentum is, though, because it's internal torques. Internal forces we don't have. We have external forces. But we only have internal torques. Like this bug is going to put a little torque on the system. So we can go ahead and derive that out by saying L of 1 equals L of 2. L1 is going to be the bug. And 2 is going to be the bar. Okay. And although I could use MVR for the bug if I want. Well, maybe I will. Maybe it'd be easier because we know the speed of it. So it's a point particle. So we're going to say MVR there, and then we're going to get we're going to set that equal to the bar, and the bar isn't a point particle, so we're going to have to call that I omega. And it's good because omega is what we want. This is a 1, and it looks like since the bug is at the end that the radii of those will be the same. I don't have to give them a special variable. Okay, this is I2 omega 2. Okay. We know the momentum, or we know the moment of inertia of the bar fixed at one end is 1/3 mr squared. So we're going to call that, look up in a table if you need to, 1/3 m2 r squared. It's nice because it turns out that it's the same r because it's at the bug is at the opposite end. We don't have to measure them differently. Omega squared. Okay. And that's m1 v r. Okay. You look at the equation. There's the same r on both ends, so I can divide one of those out. Okay. Oh, sorry, that's not omega squared. Okay. And then we can go ahead and move everything over to solve for omega. So 3 goes the other side. 3 m1 v over m2 became capital somehow. I'm not really sure how that happened. R, and that's going to give us omega 2. That's why it was squared. Okay. So I'm going to plug everything in over here. Okay. Again, we can convert it if you like. 0.01 kilograms. This one we have to convert. The 20 centimeters per second has to be converted to metric. 0.2 meters per second, all divided by 0.05 kilograms. You can see since we're dividing kilograms over kilograms, we probably could have left it as 10 grams and 50 grams, gotten the same thing. And the radius is 100 centimeters, so we're going to call that 1 meter. We divide all that, we get 1.2 over seconds. And remember, since radians is a dimensionless unit, we're going to call that 1.2 radians per second. B asks, what's the total kinetic energy just after the bug leaves? Oops. Remember that initially there was 0 kinetic energy in the system. Both of those things were not moving at all. So you're just going to take, so for the bug, I'm going to take 1/2 mv squared. And for the bar, I'm going to take 1/2 I omega squared. So that's going to be the bug. And that's going to be the bar. That's going to equal 1/2. And again, I have to have them in metric this time. 1 kilogram. And 0.2 meters per second, quantity squared, plus 1/2. Okay. And again, we know the moment of inertia of the bar is 1/3 ml squared. L is the length of the bar. Okay, again, this is 0.05 kilograms. 1 meter, because that's 100 centimeters. Okay, and that's squared. And then it's the 1.2 radians per second quantity squared. I'll just add squared. And if we do that, we get 2 times 10 to the 4th. And again, it's going to be joules. Plus, the other one ends up being 1.2 times 10 to the negative 4th joules. End up with 3.2 times 10 to the negative 4th joules. Okay. And that's part B. Part C asks, where does it come from? Okay. Well, it comes from work that's done by the bug. The bug, remember, this is part C up here. The bug is putting a force, a downward force, through a distance, and that distance is parallel to the force. So it's actually doing work on the system. Okay? And when it does work on the system, it's going to put kinetic energy in the system, in both things in this case. And that's where the kinetic energy comes from.